This lecture will cover the Rankine earth pressure theory, which is actually still somewhat commonly used for active earth pressure, not for passive earth pressure, for a reason that I'll talk about. But it's important to know what's in the theory, even though it's not used anymore for passive pressure, just for the sake of kind of history, right? So there's a number of assumptions that are made. First, we're going to assume that the backfill is cohesionless. And I'm going to why it switched tools here. Go back to this. I'm going to refer to the retained soil as backfill. That doesn't mean that it necessarily has to be a backfill. It could be native soil. All right, it could be an excavation in existing soil, in which case the soil is not really backfill. It hasn't been placed and compacted and filled. But I'm just going to call it backfill for convenience. All right, we're going to assume that there's a constant friction angle in the backfill material. All right, and so, even though we know that peak friction angle depends on confining pressure, right, we would tend to have, for a uniform relative density, a higher friction angle, shallow depths, and a lower friction angle, deeper. We're going to assume that the friction angle is constant here for Rankine earth pressure theory. We're going to assume that the wall is vertical. So you can see a diagram right here of the vertical wall. When we get to Coulomb theory, we'll give the wall an angle. And then we're going to assume a planar backfill. So the backfill itself can be inclined at an angle beta, but the wall is assumed to be vertical. And then we'll assume a planar rupture surface. All right, and this is actually the reason why we don't use Rankine theory for passive pressure. The real rupture surface is not planar, it's curved. And so this is an approximation that is reasonable for active pressure, unreasonable for passive pressure. So that's the reason we don't use it. And then Rankine also assumed that the resultant, the PA right here, so, let me just illustrate. This is the planar rupture surface inclined up at an angle theta. And so he assumed that this PA is parallel to the backfill. Sorry, I'm really struggling with this tool here. So rupture surface parallel to backfill. All right, and that's important. That a lot of the time you'll hear people say that Rankine theory assumes that there's no friction between the soil and the wall. Well, that's not technically true. If there is an inclined backfill, then the resultant is also inclined, which implies that there is a vertical component of the resultant force. Therefore, there must be some friction acting between the wall and the soil. If the backfill is horizontal, then indeed the resultant force is also horizontal, and that would correspond to a condition of no friction. All right, so we have a free body diagram. There's going to be the weight of the wedge right here. So basically this triangle that I'm sketching here is the same as this triangle in there. I'm just pulling it out so that we can annotate it. Then we'll have PA acting on this wedge. I'm drawing it equal and opposite to the direction on the left because that PA is pushing on the wall. This one's pushing on the soil. Then if we had a normal here, this is a 90-degree angle, there's going to be some kind of a resultant force there inclined at an angle phi. And so we'll call that capital R. Now, we need to do some geometry here. This angle, I'm going to annotate angles in blue so that it's easier to see. This one is 90 degrees plus beta. This one is going to end up being, this is theta down here. So this is 90 minus theta. So if we just sum up the angles, they have to be equal to 180 degrees. So this must be theta minus beta up there in that little angle. Okay, so then what we do is add these forces together to give us equilibrium. So this one's W, that's R. This one is the active force resultant. And then we need to also figure out the angles in here in order to solve this triangle that we have. So again, I'll stick with blue to annotate angles. This one is theta minus phi. This one is 90 minus beta right here, 90 degrees. And then this angle is a little bit long, so I'll write it out here, 90 degrees plus beta plus phi minus theta. And I'm just going to use phi and phi prime kind of interchangeably here. This is an effective stress analysis, right, because there's no cohesion. All right, so we have everything that we need now, all of the forces and the angles. We just need to do the equilibrium calculation to solve for PA. And what I'm going to do, I'm going to put a theta in here. This is the active earth pressure, but it's a function of theta in this case, which in the end we don't want it to be. And so we'll talk about that later. But basically, as the wall moves away from the fill, which is the active pressure, the wedge is going to form along whichever preferential angle it wants, right? Whichever one is the easiest for it to fail, that's the one it's going to pick. And of course, the surface that's easiest is actually slightly curved, but we'll get to that later. Anyway, theta should be a part of the solution, not a parameter that we specify. So it's just a little minimization problem. So anyway, we have to do some trig, right? Oh no, not trig. So here we've got this little triangle, and there's two identities that we'll use. One is the law of sines, which you can see here. Any side length divided by the sine of the opposite angle is constant for the for the triangle. And then the area of the triangle can be derived in that expression right there. So I'm going to use this area expression to compute the weight of that slice. So if we come back up here, we have some lengths. You know, this is h. We need to know the area of that wedge. So we end up with this equation for the weight, gamma h squared over 2 times some stuff, right? So this is sine terms over there using that area identity. And then by the law of sines, we can come up here and look at this PA of theta divided by this angle is going to be equal to the weight divided by this angle, right? And so that's what we have here. PA over sine theta minus phi is equal to W over sine 90 degrees plus beta plus phi minus theta. So now we can move this term over here, plug this whole thing in for W, and we end up with this kind of longish expression right there, which is PA of theta, which is the active pressure for a given failure inclination angle. And if you were to plot this function, you would see something like this diagram here, where we're plotting PA of theta versus theta. And it would come up and it would reach a peak, and then it would come back down again. That peak is the solution, all right? Because the soil, as the wall moves away, the pressure is decreasing, decreasing, decreasing. The first time that it reaches a failure condition anywhere on any angle, that's how it's going to fail. So this I'm calling PA now, not PA of theta. This is actually the solution, and there's theta critical, which is the corresponding angle of inclination of the failure wedge. And the way we solve that is to take the derivative of this fairly long expression with respect to theta, and it appears there and there and there and there. So we have to do, you know, a lot of chain rule here. Set it equal to 0, and then solve for that theta to get theta critical and plug it back into the expression, and then we would get PA. I'm not going to walk you through all that derivation. I'm just going to give you the end result. So here's the equation for PA. It's gamma h squared over 2 multiplied by this whole thing here, which has a bunch of cosine beta and cosine phi terms in it. Notice that theta doesn't appear anymore. So we've gotten rid of theta and solved for the active pressure, the maximum active pressure for any theta. So this expression right here is now our new Ka expression, right? That's for an inclined backfill where the resultant force is parallel to the backfill, and we'll call that Ka. And so our passive earth pressure, our active earth pressure resultant is equal to gamma h squared over 2 multiplied by Ka. Okay. Then we can do this for passive pressure. You know, we would have a weight here, same basic free body diagram. The passive resultant is still assumed to be parallel to the backfill, and now this resultant force flips direction to be that way instead. So there's our PP, and then here's W R PA of theta, and this would be 90 degrees. Sorry, let's stick with blue. 90 degrees minus beta, theta plus phi up there, and then 90 degrees plus beta minus theta minus phi. So very similar to what we had for active, we're just different by a few signs on theta and phi. So we go through that whole process again, derive force equilibrium using the law of sines from that, and we get this equation here where now this term is Kp, or the coefficient of passive pressure. And the only difference are the sign conventions here, right? The plus minuses have switched, and there's a minus there, and there's a plus. Well, there's a minus on top, and there's a plus on top here. Actually, let me check that. Yes, that's right. Okay. So now this is Kp, and we have gamma h squared over 2 times Kp. And I've already mentioned this, the planar failure surface assumption is not a good one for passive pressure. And as a result, you should never use Rankine earth pressure theory for passive. Okay, it's not just off a little bit, it's off a lot. So maybe a factor of 2 or more, depending on how much friction there is between the wall and the soil. You should only use it if the wall is purely frictionless, but then the curved failure surface solutions, the log spiral solutions, will also give you the right answer. So as a general rule of thumb, it's better to use the log spiral method for passive earth pressure. So this derivation was kind of a historical relic. Now when beta is equal to 0, you do have the horizontal, the resultant force is horizontal, which corresponds to a frictionless wall. And in that case, Ka reduces to 1 minus sine phi prime over 1 plus sine phi prime, which is commonly derived from the Mohr circle, right? If you have the two ends of the Mohr circle, sigma v prime is the bigger one, sigma h prime is the smaller one, you can draw a triangle and solve for the ratio of principal stresses, right? So remember, you always have principal stresses on the Mohr circle where they intersect the x-axis. It just so happens with a frictionless wall that the principal stresses are vertical and horizontal, which is why you get such good agreement here between Rankine earth pressure theory and that Mohr Coulomb interpretation. And then the Kp is just 1 over Ka, you get 1 plus sine phi over 1 minus sine phi. So these are reciprocals. And then the principal stress planes for active, the failure wedge here would be inclined at an angle of 45 degrees plus phi over 2 from horizontal. And then for passive, it's 45 degrees minus phi over 2. And once again, in reality, the failure surface might be more like that for passive. Significantly different. That's going to give you a lower earth pressure. I guess one thing I didn't mention up here, if you were to plot, this should be PP. Not sure why that just disappeared. I'm just going to make it a P because I'll delete that image again. Okay, if you were to plot PP versus theta now, you would get a solution that's the opposite of this one. Instead of coming up to a peak, it would come down to a peak, and you would do the same process to find the minimum passive earth pressure. So if you come down here, a solution that comes down like that and up, that's going to actually have a lower passive pressure and therefore is a more accurate solution than the planar surface. Let's take a look at the displacements required to mobilize the failure conditions. So if we have a vertical wall here and we move it into the backfill, that's passive. If we move it away from the backfill, that's active. And it's important to know how much displacement is going to be required to mobilize these active and passive stress states. So here I'm plotting K, which is either like Ka or Kp Or K naught, right? We've already talked about at rest earth pressure. If the wall doesn't move at all, then the earth pressure is at rest. It's the same as if the ground surface just continued forever, there would be zero horizontal strain. So here's K naught. As the walls moved away, we moved from K naught down toward Ka, which is the limit condition. That's the limit state. And it generally doesn't take a whole lot of displacement to get that Ka mobilized, maybe from 0.001 to 0.04 in terms of the displacement normalized by wall height. So that's important because if the wall moves just a little bit, you'll reduce quickly from K naught down to Ka. On the other hand, passive takes a lot more displacement, right? You have further to go. Usually K naught is pretty far away from Kp. And so, you're going to have to push the soil much further to get it to fail. So that's usually like 0.01 to 0.07 in terms of delta over H, much more significant lateral displacements. Stiffer soils will tend to be on the low end. Softer soils will tend to be on the higher end here. One more thing that I'll mention before we end this Rankine earth pressure video is that Terzaghi noted way back in 1936 that Rankine stress states can exist in their pure uniform state only if, for a horizontal fill, only if the wall is frictionless, but also the base is frictionless. And then let's just assume that the deposit ends at some rigid boundary that's also frictionless. Okay, if you have these frictionless boundary conditions, if you wanted to do a finite element model and actually mobilize Rankine earth pressures, those are the boundary conditions you'd have to use. Rollers everywhere, maybe a pin here, right? But otherwise, rollers everywhere so that there's no friction. And what Terzaghi was arguing is that that's unreasonable. How is it that you could get a frictionless boundary here? Because you've just probably compacted soil on top of soil. There's obviously going to be friction there. So if the wall is to move this way or that way, the strains are actually going to be localized in a small region there because this friction down there will cause it to deviate from the Rankine earth pressures. So Terzaghi said something like Rankine earth pressure exists only in our imaginations. It's not a real thing, and he argued back in 1936 that we should no longer be using it. And if we did have these boundary conditions, the amount of displacement required to reach an active pressure state or a passive pressure state within this deposit, that displacement would not be normalized by the height, it would be normalized by the length, because now strain would be measured like as displacement divided by horizontal displacement divided by horizontal length, just like you're testing a steel bar or something. So delta at failure would be proportional to L, not to H, which contradicts a lot of measurements that show that the amount of displacement that a wall has to go through to reach a failure condition is proportional to H. There is one exception that I found in my PhD research. If you have a non-liquefiable crust up here, maybe during an earthquake, and soil liquefies underneath it, then there's very little shear stress at the bottom. It's almost like a frictionless boundary. And if this were to spread laterally, let's say that there was lateral movement of the ground toward a foundation that's pile supported or something like that, it would actually take a lot of displacement, right? The amount of displacement of the lateral spread would have to be pretty big, much bigger than what we would assume from this sort of diagram, much bigger than 0.01 to 0.07. It might be 1 times the height or something even bigger than that. So anyway, that's an interesting thing that I just wanted to share toward the end of this video.